All right, so in this video, let's take a look at graphing rational functions. I'll have several examples. I'll do one problem per video because these videos take a while to do. All right, so this is a list of the things that we have to go through and find. We need to find our intercepts, our x and y intercepts. So remember, to find the x-intercept, you set the function equal to 0 and solve for x. And to find the y-intercept, you just plug 0 in for x and evaluate it. And that gives you your x and y intercepts. You should know how to do that. That's from algebra. All right, and then we look at symmetry. This right here is, we're going to look at odd and even functions. All right, so we know a function is odd if we can evaluate the function at negative x and we get negative f of x back. Okay, that's an odd function. If the function's odd, we know that it's symmetrical about the origin. And then if it's an even function, when we evaluate the function at negative x, we get the function back, the function itself back. That means it's an even function. That function is symmetrical about the y-axis. And then we've got horizontal and vertical asymptotes. So to find your horizontal asymptotes, you just take the limit of the function as x approaches infinity and x approaches negative infinity. And if they approach a number, then your horizontal asymptote would be y equals whatever that limit was. Okay, I'll explain it more as I'm working through the problem. And then for vertical asymptotes, you want to look at the function and see where it's undefined, where the denominator is 0. And then you need to take the limit as x approaches those numbers, numbers, you may have one or two or more. So you want to take the limit as x approaches those numbers where the function's undefined from the left and from the right. And when you take that limit, if it equals infinity or negative infinity, then that means there's a vertical asymptote there. And then you've got slant asymptotes. That you want to check that if the degree of the numerator is 1 more than the degree of the denominator. And then we've got to look for increasing and decreasing. That's where you take the first derivative, set up your number line, see where it's positive, negative. And then we've got local max, min, concavity, where is it concave up, concave down, and then any inflection points. Okay, so like I said, I know I ran down this list pretty quick. I would just copy it down, and I'm going to explain each step while we're working the problem. Okay, so it'll make more sense. All right, so let's go ahead and get started on an example. All right, so let's take a look at this example. We want to graph f of x equals x over x squared minus 4. All right, so first thing, let's go ahead and find the intercepts. Okay, so we've got our intercepts. All right, so first let's find the x-intercepts. All right, so remember, to find the x-intercepts, we're going to set the function equal to 0 and solve for x. So remember, a fraction, the only time a fraction is 0 is when the numerator's 0. So we'll take the numerator and set it equal to 0, and we just get x equals 0. There's nothing to solve there. So our x-intercept is the point 0, 0. Now, all the information that I need to use to graph this thing with, I'm going to write it in red. What I would suggest you do is the information that you're going to use, put a star beside it or something. All right, so there's the x-intercepts. Now we need the y-intercepts. All right, so in order to find the y-intercept, Well, we just simply evaluate the function at 0. And of course, that'll give us 0. I mean, we had it down here, the x-y intercept is 0, 0. That's not going to always be the case. It just is in this one. All right. So our y-intercept is 0, 0. All right, now let's look at symmetry. All right, so we're going to see if this is an odd or an even function. So to do that, we need to take our function and evaluate it at negative x. So I'm going to take the negative x and plug it in for x. So that's going to be negative x over negative x squared minus 4, which is negative x over x squared minus 4, which that's going to give us, well, let's see. It doesn't give us the exact function back. But see, if I take this negative and write it out front, then that's going to give me negative, this negative sign here, and then look at this. I end up with f of x here. So that equals negative f of x. So that tells me that this is an odd function. All right. So what does that tell me? Remember, an even function tells you that the graph is going to be symmetrical about the y-axis, and an odd function, that's going to be symmetrical about the origin. All right. So now I need to find horizontal and vertical asymptotes. So let's look for the horizontal asymptotes. So to find the horizontal asymptotes, we've got to take the limit of this function as x goes to negative infinity and as x goes to positive infinity. Okay, we're going to do both of them. So remember how to evaluate limits as x goes to negative infinity or positive infinity. If you don't really remember and you need a refresher on it, I've got some videos on that and you can go check those out. So this is equal to the limit as x goes to negative infinity of x over x squared. Remember, you just keep the largest exponent from the numerator, largest exponent from the denominator. And so this is the limit as x goes to negative infinity of 1 over x. The x and x squared cancel, and we're left with 1 over x. And so this denominator is going to negative infinity, so that means the whole fraction is going to 0. So that tells us there's a horizontal asymptote at y equal 0. So before we write that down, let's go ahead and take the limit as x goes to infinity. Now, in this problem, we'll get the same thing, and we'll do the same thing as we did just a while ago. Just keep the largest exponent from the numerator, largest exponent from the denominator. So this is the limit as x goes to infinity of 1 over x. X is going to infinity, so the denominator is getting really large. So that means the whole fraction is getting really small. It's going to 0. So that tells me I have a horizontal asymptote at y equals 0. Okay. All right. Now, it's not going to always be the case that you're going to get the same number as you go to negative infinity and positive infinity. You can get different numbers. Okay. All right. Now, let's find our vertical asymptotes. So, to find the vertical asymptotes, we want to look and see when is the denominator 0. So hopefully you can see that this is when x is plus or minus 2. Okay? So we've got to take the limit as x goes to 2 from the right. I've got to check each one. Okay? Now, the thing that you have to remember here is just because the fraction is undefined here, just because the plus and minus 2 makes the denominator 0, that does not mean there's a vertical asymptote there. That means there's a possibility of a vertical asymptote. So what we have to do to show that there's a vertical asymptote is we have to take the limit of the function as x goes to 2 from the right or from the left. It doesn't matter, either one. And we just have to show that that equals infinity or negative infinity. And then that means there's a vertical asymptote there. All right, so for this limit, so I'm approaching 2 from the right. So that means that what's happening, and I'll explain this one in detail, and then the other ones I'll just, it's a similar thought process. So I won't explain it as much, but I'll go over this one in some detail. So we're approaching 2 from the right-hand side. So that means that we're plugging numbers in like 2.1, 2.01, 2.001, and so on. Okay, getting closer and closer to 2 from the right-hand side. So one thing I want you to agree on is that the numerator, as we're getting closer and closer to 2 from the right-hand side, that the numerator is pretty much going to be 2. Okay, I think we can agree on that. But look what's happening to the denominator. See, if I plug 2.1 in and square it, that's going to give me like a 0.1 or 0.01 in the denominator. Let's see. So I'm going to get 2.1 squared minus 4. Now let's see, 2.1 squared, and then minus 4. So that's actually going to give me 2 over 0.41. And then if I do 2.01 squared minus 4, that's going to give me a 0.0401 in the denominator. Okay, and then if I put in 2.001, what I'm wanting you to see is how the denominator is getting smaller and smaller, but the numerator is pretty much staying at 2. All right. So what that means is if the denominator is getting smaller and smaller and the numerator staying at 2, that means this is going to infinity. Okay, so that right there shows there's a vertical asymptote at x equal 2. We don't have to do anything else for 2, but we're going to. We're going to take the limit as x approaches 2 from the left. Okay? Now, why am I doing this? I don't have to do this to show that there's a vertical asymptote. So why am I doing it? Well, because I got to know how to graph this thing. So as I'm coming into 2 from the right, and then I'm going to come into 2 from the left, I need to know where the graph's going. That's why I'm doing it. Okay? And the same thinking as the first part, I'm putting in numbers like 1.9, 1.999, and you can see the denominator is going to get smaller and smaller, but it's going to be negative. And the numerator is going to pretty much be 2, so this is going to negative infinity. And then we're going to do the same thing as x approaches negative 2 from the right. All right, so look at this real quick. I've got negative 2, and if I'm coming in from the right, see, here's negative 1. So I'm plugging in numbers like negative 1.99 and stuff like that. So this is going to be negative infinity. And then the limit as x goes to negative 2 from the left, I'm coming in from this side. Remember, there's negative 3, so I'm plugging in numbers like negative 2.001, and so that's going to be positive infinity. So I've shown that there's a vertical asymptote at 2 and at negative 2. So my vertical asymptote is x equal negative 2 and x equal positive 2. Okay? And then there's no slant asymptotes in this problem. So now what I have to do is I have to find where it's increasing, decreasing, local max min, concavity, and inflection points. All right. So what I'm going to do, I'm going to rewrite the problem right here. That's x over x squared minus 4. Okay. So now we've got to take the derivative to find increasing, decreasing, and local max and mins. We've got to find our critical numbers. So I've got f prime of x. Now for the derivative of this, I've got to use the chain rule. So I'm sorry, not the chain rule, the quotient rule. So that's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared. All right. So if I simplify this, I get f prime of x. That's going to be x squared minus 4 minus 2x squared over x squared minus 4 squared. So f prime of x, that's going to be what? Negative. And that's going to be what? X squared plus 4 over x squared minus 4 squared. All right. So now for our critical numbers, that's where the first derivative is 0. Okay. So if I set this equal to 0, remember that a fraction is only 0 whenever the numerator is 0. And hopefully you can see with this, that's never going to be 0. Because in order for this to be 0, this term here would have to be negative 4. And there's nothing you can, there's not a real number you can square to get negative 4. Okay? And then the next thing is, the critical numbers, is where the first derivative is undefined. All right? So the first derivative is undefined whenever the denominator is 0. So of course that's x equal plus or minus 2. But these are not critical numbers. And why are they not critical numbers? Because they're not in the domain of the function. Because they would also make the function undefined. Okay? All right. So we have no critical numbers. So what do? Well, whenever you're looking for increasing and decreasing, and this is going to go for when we do this, when we look for concavity too, and we have to do the second derivative, the same thing's going to apply. But whenever you're looking for increasing and decreasing, you plot all your critical numbers on the number line, okay? And you also plot where the first derivative is undefined, even though these are not critical numbers, because it can change increasing and decreasing at these numbers. It's just that if it does change increasing and decreasing at these numbers, there's no local max or min there, because you can't have a point, because if you plug 2 or negative 2 back into the original function, it's going to be undefined. But we test it out. So we've got negative 2, we've got positive 2. This is going to break the number line up into 3 intervals. So I've got x equal negative 3, x equals 0, and x equal 3. All right, so remember, I have to evaluate the first derivative at each one of those numbers. And so here, if we look at it, we don't even have to think about this any, do we? Because look, do you see this numerator here? It doesn't matter what number you plug in for x, that numerator is going to always be positive because it's something squared and then we're adding 4. Okay? And then if you look at the denominator, well, this can be negative, but then we're squaring it, so the denominator is going to always be positive. You see that? So if the numerator and denominator is always positive, that makes it a positive, but then I've got this negative sign out front, so that means the first derivative is always negative. Okay? So what that tells us is that this thing is decreasing the whole time. And I'll go ahead and show my work here. Okay? So if you plug in the -3, the 0, and the +3 back into the original function, you're going to get negative. So this thing's is decreasing the whole time. All right. So now let's write down this is decreasing. Now, on this decreasing, yes, look at this. It's decreasing from -infinity to +infinity. But we don't want to write that. We want to break this up as decreasing from -infinity to -2, -2 to 2, and 2 to infinity. And the reason we want to do that is because if we write -infinity to infinity, then we're including -2 and 2 in this interval. And that's not the case because the function's undefined there. So we break this up into the intervals to leave out the -2 and the 2. Okay? All right. And then, well, we can go ahead and write here, no local max or min. Okay? So there's no local max or min. All right. So that wasn't too bad. So now we've got to do concavity. Okay? Where is it concave up? Concave down. Erase those. So to do that, I need the second derivative. So I've got to do the derivative on this. That's going to be quotient rule. So let me just rewrite this first derivative with the negative out in front. All right, so let's take the second derivative. So the second derivative is going to be negative, and then that's the derivative of the numerator times the denominator minus the derivative of the denominator, which is 2 times x squared minus 4, subtract 1, times the derivative of what's inside the parentheses, times the numerator. And so that's over x squared minus 4 squared squared. And so I get the second derivative, and I'm not going to work all this out. You can do it. I'm just going to write the answer down to save some time. This video is already going to be long enough. All right, so this is what you would get for the second derivative after you simplify this. So now for concavity, we've got to take the second derivative and set it equal to 0. And remember, the only time that a fraction is 0 is when the numerator is 0. So that means that I'm going to have 2x, let me come down here and do it, 2x equals 0, which tells me x is 0. All right, so why did I just take the 2x and set it equal to 0? Well, x squared plus 12 will never be 0. The only term that can be 0 is this one right here. Okay? So now, on my number line, I need to plot 0, but then I also need to plot -2 and +2 because that's where the second derivative is undefined. Okay, you want to test those points also. So I'm going to use x equal -3, x equal -1, x equal 1, and x equal 3. And so now we will do, let's see, f double prime of -3. So that means I'm going to plug the -3 into here. All right, so let's see. This is always going to be positive up here in the numerator. So if I plug the -3 in, that's a negative, a positive, and a positive. So that makes the whole thing negative. So that means on this interval it's concave down. And then I've got to do f double prime of -1. So that's negative, positive, negative. And so that's positive. So that's concave up. And then I've got f double prime of 1, positive, positive, negative. So that's negative. So that's concave down. And then f double prime of 3. That's positive, positive, positive. So the whole thing's positive. So that's concave up. And so I've got concave down from -infinity to -2 and 0 to 2. And then I've got concave up from -2 to 0 and 2 to infinity. All right. So there's my concavity. Now I've got to look at inflection points. All right. So remember the inflection points, that's where the graph changes concavity, where it changes from concave up to concave down or concave down to concave up. Well, it changes concavity at -2, 0, and 2. But there's not an inflection point at -2, and there's not an inflection point at 2. So if you remember, our function is f of x equals x over x squared minus 4. Okay. Well, if I plug in the -2 or the 2, I get 0 in the denominator, so you can't have a point there. It's undefined. So my only inflection point is at 0. And then remember, to get your y-coordinate, you take the 0 and you have to plug it back into the original function to get your y-coordinate. And so when I plug the 0 in, I get 0. And so there's my inflection point. Okay. So now we found everything we need to find. So now we can graph it. So I'm going to erase some of this stuff and move some stuff together, and I'll pause it while I do that, and then I'll come back and graph it. All right, so let's look at all the information that we have and see about graphing this thing. So I've got my x and y intercept. So what I like to do is just go ahead and plot my points. So let's plot the point 0, 0. That's my x and y intercept. And then look, remember this, that's our inflection point. So that's plotted also. And then what I like to do is I like to go ahead and draw in my asymptotes. So I have a horizontal asymptote at y equals 0 and vertical asymptotes at -2 and 2. And so I have a horizontal asymptote here. And then I have vertical asymptotes at 2 and at -2. So this is -2 and there's +2. All right, so now we can look at everything else, the increasing, decreasing, concavity, to help us draw it. All right, so let's look at this. All right, so it's decreasing from -infinity to -2. So as I'm coming from over here, -infinity to -2, this thing's decreasing. Okay, it's decreasing. Well, how's it decreasing? Is it coming up here? Is it going here? What's it doing? Well, let's look and see. Well, and I erased it. Let me put that back. All right, so this right here is what I accidentally erased this. We need these limits here. So it's decreasing as I'm coming into -2, but let's see what it's doing. As I'm coming into -2, now I'm coming in from the left. Well, where's it going? It's going to -infinity. You see that? It's going to -infinity. And then the other thing that I erased, I actually erased the limit as x goes to -infinity of the function. That's 0, remember that? and the limit as x goes to positive infinity of x over x squared minus 4, that equals 0 also. So you can see as I'm coming into -2 from the left here, okay, I don't know, I might have said right earlier, I meant left. But as I'm coming in from the left-hand side to -2, I'm going to negative infinity. But look, as I'm going to negative infinity this way, it's approaching 0. And so that tells me that my line is going to look like this. Okay? Now, let's look in here. So now we're between -2 and 2, and that thing's decreasing. And then also, if you look from negative infinity to -2, it says that it's concave down, and so we have it drawn concave down. So now let's look. As we're coming in to -2 from the right-hand side, well, our graph is going to infinity. You see that there? Okay. And then look at this. From -2 to 0, so from here to here, it's also concave up. So that tells me it's going to look something like this. But look what happens when it gets at 0. From 0 to 2, it changes to concave down. And I can also see that as I'm approaching 2 from the left-hand side, I'm going to negative infinity, so that tells me it's going to go this way. Okay. Now for this one. Well, as I'm approaching 2 from the right-hand side, this thing's going to infinity. And as I'm going to infinity, well, it's going to 0. And on this, it's what? It's concave. From 2 to infinity, it's concave up. And of course, the graph is decreasing the whole time. So this graph is going to look like this. Okay. Now, the other thing that, I didn't use on this one, but we know it's an odd function. But see, we could have just drawn this part of the graph and this part of the graph, and then just mirrored this about the origin. Okay. And we could have got this side over here. But what I'd like to do, I like to go back and look at all this stuff here, these limits that I found. And that tells you exactly what the graph is doing as it's coming into each one of those asymptotes. That's why you need to find the limit as x approaches 2 from the right and the left. You know, whatever makes that rational function undefined, you need to find the limit as it's coming into that number from both sides so you know how to draw the graph. And yes, in order to show that there's a vertical asymptote, that's all you got to show is this first one. You don't have to show this. We did this. We're doing this because we need to know what the graph looks like. And then the same thing here as to show that there's a vertical asymptote at -2. Well, we didn't have to show both of these. That's all we had to show was that first one. And that's good enough to show that there's a vertical asymptote there. Okay. All right. So I hope this video helped. Check out my other videos. Give me a like, share, and subscribe. And thanks for watching.